Okay, this video is going to be an introduction to topic 7/17, which is equilibrium. So the term equilibrium or dynamic equilibrium or the equilibrium state refers to when you have two processes that are occurring at the same rate, but they are opposite to each other. And the fact that they're opposite and occurring at the same rate means that they cancel one another out. So overall, there are no changes in the observed amounts or concentrations that are involved. So for us, we're always going to represent equilibrium with a set of double arrows, usually drawn like this. Okay? But you could also draw it with two arrows like that. This is the way you'll see it. So equilibrium means that the forward and reverse processes are both taking place at the same rate, and that's what is equal about equilibrium. There are two equal and opposite rates. The amounts that are on either side of this arrow do not have to be equal. That's a common misconception, but the amounts and concentrations in equilibrium do not have to be equal. So I'll continue to point that out. There are a number of examples of physical equilibrium that you probably are pretty simple to recognize and think about. So changes of state, you can have two states of matter that are in equilibrium with one another, where both phase changes are occurring. So you can have evaporation and condensation, you can have freezing and melting, and the amounts of the liquid and solid or the amounts of the liquid and gas don't change, but the two different processes are continuing to occur. And some evidence of that is if you did, for example, the solid-liquid equilibrium, the solids might change shape over time, but the total amount that is solid would not change over time. That would be evidence that something is still taking place even though the amounts don't appear to change. Another physical example is if you have a saturated solution where you've dissolved a lot of salt or a lot of sugar into water. It could be any solvent, but usually we deal with water. And so you've got some solid solute that's just sitting there at the bottom. And at the surface of that solid, particles of solute will continue to dissolve, while other particles of solute that are dissolved will continue to recrystallize. And so those two processes, dissolving and recrystallizing, will be equal and opposite. And so over time, the shape of the solid might change, but there's actually no change in the mass of solid that is dissolved. Now, for the first time, though, you may be hearing that chemical reactions can actually go forward and backwards. Many reactions that we've seen thus far do not do this, and so this hasn't really been relevant yet. For a lot of reactions, they do go to completion. So they react, and eventually you use up some reactants, and they never return back to the original reactants. So reactions like combustion are not reversible. They are not reactions that go to equilibrium. They only go in one direction. But there are plenty of reactions that as you start to make products, the products then start to react and turn back into reactants. And so eventually those can occur at equal rates, and then you're at a state of chemical equilibrium. So whether it's a physical or a chemical equilibrium, you need to have a closed system if equilibrium is to occur. And that essentially means that you're closing off the system, the reaction, or the process from exchanges of matter or energy from the surroundings. And that allows the equilibrium to occur. Okay, so you can have equilibriums between solid and liquid, so that would be melting and freezing equilibrium. You can have equilibrium between liquid and gas. That would be equilibrium that is vaporization and condensation. And you can have it actually between solid and gas, which would be sublimation and deposition. So any of these can occur. Now, if I have a jar or a glass or a beaker of water, let's pretend that for an instant there's no gas particles of water above the water itself. So we know that water would spontaneously begin to evaporate, and so particles of water would start to leave. Now, in this situation, we have an open container. Forgive my trackpad writing. We have an open container, which means that as the particles leave, nothing keeps them in there. And so even if they bounce into the walls, they're then going to bounce off, and they're all going to just leave. So this is an open system. Eventually, if you leave a jar of water out long enough, all the water will evaporate out of that jar. It obviously helps if it's hot, if you're in a hot place. But even if it's relatively cold, given enough time, if it's months or years, eventually all the water will evaporate. Because it's open, so eventually this process of evaporation will be overall favored, and you'll end up with an empty jar. But if you put a lid on there and you close it, then there will always be water in there. No matter what, there'll always be some water in here because it's a closed system. So it's pretty simple to imagine that as water particles begin to evaporate and fill up the space above here, so if I start to draw in little gaseous water molecules that we couldn't actually see, well, eventually, as you fill up this space with water molecules, it becomes very common for these water molecules to recondense. So when particles bounce back into the liquid, some of them are going to recondense. And so eventually you get to a point where the rate of condensation is exactly balanced out by the rate of evaporation. And so at that point, you would no longer see any change in the volume that was liquid and the amount that's gas. Okay? So you can have an equilibrium between phase changes, but only if you close off the system. Okay? And so one common thing is to look at graphs related to equilibrium. And so if we want to think about the number of particles over time, and now we're going to focus just on the closed system at the right. At the beginning, we had a lot of liquid water. So liquid water amount is quite high, but it goes down over time. It doesn't go to zero, and eventually it levels off when it reaches equilibrium. On the converse, we were pretending we started off with zero gaseous water, and then as evaporation picks up, you start to get more and more gaseous water, and then eventually those rates start to even out, and they both level off. And so where the two graphs level off and stop changing, when the amounts stop changing, that's when you have reached equilibrium. So this green line represents equilibrium here on out, okay? Because now we can see the amounts aren't changing, and the amounts aren't changing because you have equal and opposite rates occurring. Notice the amounts of particles in each phase are not equal. They don't have to be equal in equilibrium. Only the rate of change between the two different things is what's equal. So the number of particles is not equal. If we were to draw a graph, though, that represented rates of change, then eventually the graphs should equal each other. So if I start off with the rate of evaporation being quite high, the rate of evaporation is high, and it slows down a little bit as we start to lose water. And the rate of condensation begins very slow, but picks up as there's more and more and more gas particles in there, and eventually the rates are even. And so where the rates meet each other, after that we are at equilibrium. So it depends on if the IB were to throw at you like a concentration or a number of particles graph versus a rate graph, because equilibrium means that the rates are equal. So either the amounts stop changing or the rates actually physically touch, and that would represent equilibrium on a graph. Okay. Besides just understanding what equilibrium is, the key concept of the equilibrium topic, especially for standard level, is something called Le Chatelier's principle. And Le Chatelier's principle says that a system at equilibrium, when subjected to a change, will respond in such a way as to minimize the effect of the change. Essentially, if you take a system at equilibrium and you stress it in some way, so you temporarily open that system, you either add more reactant or product, or you remove something, or you change temperature, or you change pressure. Those are all various things that we're going to refer to as stresses. And so if you add a stress to the system, there will be a resultant shift in the equilibrium, where as a result of the shift of the stress for a short time, the two rates are not equal anymore. And therefore, one of the rates is going to be faster for a while, and that's going to change the balance of the two sides of the equilibrium. So it might mean a shifting to make more of a certain phase, or a shift to make more product or reactant. Eventually, equilibrium gets reestablished, but for a time, they are out of equilibrium. And so the stress is what you do to the system, and the shift is what happens as a result. Okay? So for example, with this physical one, right? If we had the same system, and now we're going to imagine that it's at equilibrium already. So we've got the equal and opposite changes occurring, evaporation and condensation, and there's lots of gaseous water up there. If the water is warmed by 20 degrees Celsius, then which of these rates would that favor more? Well, you probably have some sort of intuition that warming the water up, so essentially adding heat, is going to favor evaporation. The hotter the water is, the more likely the water is to go to the gas phase. And so if we had that graph where they were going along hunky-dory, let's start it from here, and this is where they equalized. We had our two different rates. Well, they're equal for a while. They're at equilibrium. Everything's fine. When we add the stress, temporarily the rates would not be equal anymore. And so what would happen is that heat up would make the evaporation rate go faster. Okay? It doesn't really make condensation go any slower, but it just doesn't really help condensation in the same way that it helps evaporation. But what would happen is, as you start to evaporate more and more and more, and you fill this space up with more and more and more gaseous water, that naturally has the impact of causing the condensation rate to increase also. And eventually you will reach a point again where the two rates are equal. You'll have a new equilibrium. So we had equilibrium when the rates first met each other, and then we have a new equilibrium when the rates meet each other again. Notice, though, it's not the same equilibrium as before. In this situation, we'd have a lot more gaseous water because the rate of evaporation was faster for a while. So when you have a stress, then the system tries to reestablish equilibrium, and so you get a new equilibrium. Also notice that by increasing temp, we increased the endothermic process, or we shifted in the endothermic process. Okay? So the evaporation requires heat energy input. To make a liquid go to gas, that is an endothermic process. To make a gas come to liquid is an exothermic process. And so one of our rules with these stresses is that anytime you add heat or you increase something's temperature, that will always help out the endothermic process more than it helps out the exothermic process. So it makes the endothermic change go faster for a while. And so that's why evaporation started going faster than condensation until eventually they equaled each other back out. Okay? A couple other stresses. If we added a bunch of gaseous water into the space above the liquid, so if somehow we had a little pump and we filled this space up with lots and lots more gas particles, well, for a time, the condensation rate would pick up and be faster than the evaporation rate because you'd have all this really high pressure gas in here. And so what we would see in this instance is, again, this is our original equilibrium. And then when the stress is added, if they pumped in so much gas, then the rate of condensation would pick up for a while. And then it would begin to, I guess that's kind of an incorrect graph. Let me erase what I just did there. What would happen is immediately it would spike up, and then as the gas began to turn into water, it would sort of decrease again. And the evaporation would increase as you added back more water, and eventually they would even out. Now, don't get too hung up on these types of graphs where you have to graph what happens when a stress is added. You will never have to do that. I'm simply doing it to sort of give you a sense of how these rates would change. So I'll write it out instead. It might be simpler. So more gaseous water would increase condensation rate because there'd be so much gaseous water up there. It would be more likely to collide with the water and re-liquefy. So more gaseous water would increase condensation rate for a time, but eventually new equilibrium is established. Okay? So I think that's enough for now. I mean, that the basic idea is what equilibrium is, what dynamic equilibrium is, and that when you add a stress, the system naturally gets knocked out of equilibrium, and one of the rates tends to speed up much more than the other as a result of the stress. But eventually it just naturally sort of rights itself. So those are a couple stresses to think about. There's some other physical ones we can think about in class. And then the newest idea of all is that this can occur for chemical reactions. And so a classic example is the Haber process, the conversion of nitrogen and hydrogen to ammonia. And when nitrogen and hydrogen are forced to react and turn into ammonia using this iron catalyst, that doesn't go to completion. In fact, even under very extreme conditions, only a 15% yield is obtained. So most of the substances remain as reactants, even when you use extreme conditions. And so the reaction container ends up looking like something like this, where you've got lots of hydrogens and lots of nitrogens and some ammonias in there as well. But all of those things would exist in the container together. And so I think we'll leave it at that. We'll talk about stresses and shifts with chemical equilibriums when we have class.